better visible? Maybe. All right. So let me start by showing you a little bit of the video to give you a little bit of a motivation. So you by now you know what is explicit Euler and implicit Euler, right? What are the pros and cons of each? Explicit Euler is very easy to implement. It's very fast, but sometimes it blows up, right? Implicit Euler is the other way around. It's very stable. It almost never blows up, but it's much more complicated. You end up solving linear systems, and the linear system is changing every step. I will. Oh no. No video. Well, I can also get it this way. So this is a demo video for the system we presented at SIGGRAPH Asia 2013. So this is a very recent technique. Nevertheless, it's still a very basic thing. Just different way how to solve the implicit integration problem. So here is just showing like a nice eye candy. You know that mass spring system can be used to all sorts of things. So here it was used to cloth simulation. And that's the interesting thing. It will make more sense when I actually explain it. You can solve it not exactly with our method. Like the more iterations you give it, the better solution to the implicit Euler times that you will get. But the cool thing is that even if you do just a few iterations, the results already look reasonable, as you can see there. And as we are increasing the number of iterations, they are getting better and better. They are converging to the exact implicit Euler solution. Remember, that's what Tintin covered the last time, that the implicit Euler step can be written either as a minimization problem or as solving a system of nonlinear equations. Either way, you need to employ Newton's method to find the solution. And that's what we, of course, compare to Newton's method. So Newton's method with one iteration is equivalent to the Barov-Witkins famous paper, 1998, right? It wasn't the first to use implicit integration, but still the most famous one, the most frequently cited one for implicit integration. And if we compare it, we can see that we get very good results with less accuracy than Newton by allowing only less iterations, by terminating it early, but not having it converge until the exact result, but terminating it early, it still gives us nice results. This is, by the way, also like the beautiful thing about physics-based animation. All these wrinkles on the cloth, they just emerge, right, from the simulation. All this is using is the spring energy potential, the Hooke's law, which we were discussing before, and it was also the assignment number 1, and we were computing the gradient and Hessian of the spring. So the spring, the Hooke's law, is everything you need to get these nice wrinkles there. This is comparison to position-based dynamics. Position-based dynamics I will cover in the next class because it's also your second homework. Position-based dynamics is a very cool technique, but we are showing that it is a little bit more difficult to set the parameters for it because it introduces some non-standard parameters. And this is, again, the versatility of mass spring systems is great because it can be used to simulate all sorts of things. You can do these brittles on the brush. You can also do arbitrary stiff systems. As you will soon find out if you haven't already on the Jello, the stiffer it becomes, the more difficult to simulate things is. And this is just showing that the method has some limitations compared to the exact solution. On situations like this, we can miss some wrinkles because we are sort of only approximating the implicit Euler solution. Oh yeah, and those are Tintin's favorite examples, torturing tetrahedral animals. This is still a mass spring system with springs inside. There are tetrahedra inside the frog, and they are springs, right? So you can just shoot it away. Just Tintin's favorite example, shoot away the frog. It's just basically one springy frog, right? So if you release it, just flies out. All right, so that's the demo. So how it works. So let me explain you how it works. Let me start a little bit with a recap of the basic things, because I think it can't hurt to. Oh, let me actually calibrate a little bit better. Does look good. All right. So mass spring systems, you now should know fairly well. So let me just quickly recap the basic principles there. Actually, I can make it still bigger, right? Like that. Better? Oh, and I can turn on the light. It's always easier to tell somebody what to do, like I was telling Tintin, hey, you didn't turn on the light, rather than actually doing it. So mass spring system, we have these point masses, right? Points. So all the mass in the system is actually lumped at these points, right? So you can feel that this is not really the best what we can do. Finite elements methods are more accurate than that. But as you have seen, mass spring systems work pretty well. So even in spite of this approximation, we can still get some very nice physical behavior. And then we have the springs, which are connecting the particles, right? In whatever way we decide, right? It doesn't even have to be a tessellation of a plane. We could also easily put there a spring like this, right? I think that's what you are probably playing with now in the cello cube simulation. So this is discretization of the space. It could either be in R2 or R3. And then we also have discretization of time. So this is spatial discretization and temporal discretization. That basically means that we are interested in getting the state of the system in discrete time steps, T1, T2, and so on, right? And the difference between the two times, Ti plus 1 minus Ti, is usually some constant h, where h is something like 1/30th of a second, right? If you want a 30 frames per second simulation, that's what we did for the video, 30 frames per second. And what are we computing in every time step? We are computing the state of the system. So let me denote it as Qn. So that's the state of the system at time n, or at time step n. So let me write it down. So if I have m particles, let's say that I have m particles here. See that? Yep. So then the state of the system is going to be a 3m-dimensional vector, because I have three, let's say I'm in R3 in 3 dimensions. So I have 3 coordinates for every particle, x, y, z, right? So this is the system state at time Tn, right? And let's assume our forces are purely position dependent. To simplify the exposition a little bit, you know that we can also have velocity-dependent forces like damping, and we can also have time-dependent forces, but most important are the position-dependent only forces. And the Fqn, so if I give it a state, it tells me all the forces acting on all the particles, right? So get a better pen. Pretty much everything that could go wrong went wrong. And you also know that the forces are defined as the negative gradient of a potential energy, right? Potential energy, here I'm basically just recapitulating what you should already know, because it will serve us as foundations for the new method, which I want to explain. So this is energy potential, or energy or potential function. And the relationship between the forces and the energy is the gradient, the negative gradient to be specific, right? The other thing we need there is a mass matrix. So what is a mass matrix? Mass matrix is a matrix, in this case 3m by 3m matrix. And how does it look like? It's very simple, it's diagonal. So what does it have on the diagonal? There is m1, m1, m1. It's the mass of the first particle, right? Then there is m2, 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 just the mass of the second particle, and so on, up to mm. I don't want to write. Maybe yeah. There is a more elegant way of writing this, so I don't have to be like copying it every time 3 times. You can write this using the Kronecker product, which will be useful to simplify some of the formulas later in this algorithm. Do you know what is the Kronecker product? Did they tell you that? Did I tell you that at the linear algebra classes? There? No, not here. So the Kronecker product is not a big deal. In this particular case, or I can tell you even what is it in general. If I have 2 matrices, A and B, then the Kronecker product, usually denoted like this, means that I take every element of A. So if A is A11 up to A1, let's say n, AM1, AMN, then the Kronecker product is simply taking every element of the A matrix multiplied by the B matrix. So A11B, A1NB, AM1 times B. So this is just a matrix scalar product. A, M, N, B. And why do I want the Kronecker product there? Maybe you can already see it. If I say that I3 is a 3 by 3 identity, 1, 0, 0, 0, 1, 0, 0, 0, 1, then this mass matrix can be nicely written as this mass matrix tilde Kronecker I3, where the M tilde is just M1, M2, and so on. You see that? Because all the Kronecker product does, it replaces every number in the matrix by the 3 by 3 identity scaled by that number. So that's exactly what I want here. And it will be also useful in the following. That's why I'm sort of bothering you with this already. Okay? So this is how we got the mass matrix. And now we can quickly recap how the explicit Euler integration works. Now we have everything set up. I can denote Vn. Vn are going to be velocities of all the particles. Velocities at time step Tn. How are the velocities computed? You should know this by now. 1 over h Qn minus Qn minus 1. Oh, this is h. This is n. So the velocities, I don't really have to put them in the state if I say that they depend on the states using this backward difference formula. All right? I think so far it's pretty simple. So stupid, I really need some bigger chair here. I'll try this. So how does explicit Euler work with this setup? Probably already seen it many times, so just write it down. So we are at time Qn, and we need to compute Qn plus 1, right? So the Qn plus 1 is Qn plus h times the velocity. H is my time step. And I update the velocities as well, so it's going to be Vn plus h must inverse Fqn, right? So this is explicit Euler because the next state, Qn plus 1, is computed directly from what I already had before, right? I had Vn before, Qn before. I can compute the F from what I had before, and that's just basically, I just compute it directly, right? And there's lots of these variations. There are the Runge-Kutta methods, which are essentially variations on the same idea, except that they sample it not just at the previous step, but they sample it at many more small substeps over there. You're really refocused, right? Let's do this. Better? All right. And as you know, the explicit Euler is very simple to do, but sometimes it just explodes, right? Because there is... Why does it explode? Because if something gets overstretched, the explicit Euler overcompensates, overshoots, right? And if it overshot at one step, then the response in the next step is going to be overcompensate even more, right? So it is like oscillating more and more, and eventually it just goes out of the window. The solution to this problem is implicit Euler, or backward Euler. Sometimes this is called the forward Euler, and this is the backward Euler. Forward because that just means we directly move forward. And the backward one uses these formulas. Qn plus 1 is Qn plus h. What is here? You tell me. Vn plus 1. And Vn plus 1 is Vn plus h m inverse f from exactly Qn plus 1. So this really is the only difference, right? Notice, compare these two schemes, explicit Euler and implicit Euler. The implicit Euler really is making the step using the state it will get to after the end of the step. It sort of sounds funny, right? But that's really what it is. That's why it's called implicit, right? Here, the Vn plus 1 and Qn plus 1, they are unknowns here. So it's not just like computing something and advancing the state right there. I really have to solve for Qn plus 1 and Vn plus 1. Now, these depend on Q's, so I can also be solving just for Q's. So let me do that actually right now, so I'm not confusing you with both Q's and V's. So note that the velocity, as I said before, depends on the state like this, or I can define it to be dependent on the state like this. So if I evaluate the same formula at time step n plus 1, I will get Qn plus 1 minus Qn, right? That's really the same formula, except that I put there n plus 1 instead of n. And now what I can do, I can plug these formulas in here. So let's see what happens if I put them there. So let me first multiply it by h. So I take this formula and multiply it by h. Vn plus 1 equals hvn plus h squared. Not a big deal, right? Fqn plus 1. So now I have here hvn plus 1 and hvn, so I can plug in these guys, right? So what I will get here is Qn plus 1 minus Qn. That's applying this first equality. And, oh, let me do it slowly. Let's take baby steps. Qn minus Qn minus 1. So here I plugged the second equation, okay? But it follows. And I still have this. I still have the plus h squared m inverse f at Qn plus 1. So if I put it all on the left-hand side, what I will get there is Qn plus 1 minus 1 Qn, and this is minus second Qn, so it's minus 2 Qn plus Qn plus 1 equals h squared m inverse f Qn plus 1. All right, I just put this on the other side. Oh, did I do it wrong? Oh, yeah, of course, sorry. No, I actually did it on purpose to test if you are paying attention. No, I didn't. So this is interesting, what is on the left-hand side here, right? What is this? Can someone tell me what it is? How do you interpret it? There is a very nice word you can use to characterize that. Hmm?
Almost looks like a square or something.
This, have you ever seen this stencil? 1 minus 2, 1. This
Something
is
minus something square.
Yeah, it's related to that, but this is a discrete approximation of second derivative. Just like this is a discrete approximation of first derivative, right? The Vn, if I put the h on the other side, is 1 over h qn minus 1. This is nothing but the discrete approximation of first derivative, right? And second derivative is nothing but a derivative of a derivative. So this is a discrete approximation of a second derivative of this state. So what is the second derivative of this state? Acceleration, exactly, yeah. So this basically, you can see there directly Newton's second law, right? This is basically acceleration, and this is forces divided by mass, right? So this really, this is nothing but the famous F equals ma, Newton's second law. And how are we using it here? So we are at a state n. So we have the state qn. We of course have the state qn minus 1 from before, right? Modulo some initialization. When you start a simulation, you have to provide it some initial conditions. What velocities and at what positions is the system starting? And the task is to compute what is going to be qn plus 1, right? So this is known. This is also known. This is known, and this is known. Qn plus 1 is unknown. H and m, of course, is known, right? So the Qn plus 1 is the only unknown there. So the task of implicit or backward Euler is to basically solve this system of equations, right? You always have to keep in mind this is a system of equations because Q is a 3m dimensional vector. On the left-hand side and on the right-hand side, I have a 3m dimensional vector. So this is a 3m equations, right? So let me simplify the notation a little bit to make the formulas a little more palatable, if you will. So because both of these things are known, I can just aggregate them. So I can define a new variable y to be, by definition, 2qn minus qn minus 1. And I can say that the unknown, so I explained before that the unknown is qn plus 1, right? That's what I'm solving for. So I will just denote it as x. That's what we usually denote unknowns with, right? So this is going to be my qn plus 1. So this formula becomes, with this new, more concise notation, it becomes x minus y equals h squared m inverse f of x. So what is the physical interpretation? How would you interpret the y? Actually had some we had a little bit of fights with James. He didn't like the y notation, but I always like firmly hold the stance that the y makes a lot of sense because I believe it does make sense. How would you interpret the y? Here it looks a little bit artificial, right? You just multiply this by 2 and this by minus 1 and sum them together. Why would you want to be doing that? Maybe Tintin explained that the last time. Do you have any idea? Well, let's take a look at it. What does this mean? I could also write it like this, right? I could also write it as qn plus qn minus qn minus 1, right? Now, what is qn minus 1? Remember this. Aha, this is my hvn, right? So this is qn plus hvn, right? So what is it? What is the y? Now you should see it. It is explicit Euler step, but without any forces, right? This is the pure inertia motion. This is actually, let me see. This is exactly Newton's first law. What does Newton's first law say? Newton's first law says that if there are no forces acting on the system, then the system just continues moving linearly, right? If I have like a space shuttle, something that's somewhere far away from all gravity, and it has some velocity it's moving with, well, it's gonna be moving with this velocity forever, right? And that's exactly it. If we don't have any external forces, this is absolutely perfect simulation, right? So in other words, the y term could be interpreted as inertia term, where the inertia dictates my system to move, right? There's another. This is sort of deeper than that. You can think about it as a battle between the forces and the inertia. The y is the inertia term. So imagine I'm like a train or something heavy and it's moving, right? So it will keep moving according to Newton's first law unless there are forces acting on it, right? If I want to change the motion, I need to act on it with forces. Those are the forces. And this equation, Newton's second law, it describes the balance between inertia and the forces, right? Okay, but the main point is of this lecture is how to actually solve this. So I can make another very innocent modification. I can just multiply with m and put it in this form, and x minus y equals h squared fx, right? That doesn't change a whole lot. Again, both sides are 3m vectors. So this problem means solving a system of 3m nonlinear equations. Why are they nonlinear? If they were linear, you would just call your favorite linear solver, right? And you'll be done. But they are not linear. Why are they not linear? Maybe that's a stupid question. Because the f is not linear, right? Because the forces, even in our super simple mass spring system, even just using the Hookean potential, f is not linear forces, right? That's really all the problem in physics-based animation. That's the root of the problem, that these forces are nonlinear. And in some cases in physics, we can approximate them by linear forces, like linear elasticity. But then we lose other properties like rotation invariance. Okay, we'll get there later. So I'll save that one for later. So we want to solve this. I think Tintin already said before that solving the system of 3m nonlinear equations is equivalent to finding critical points of the following function, of function g of x, which is 1/2 of x minus y transpose m, x minus y, plus h squared e of x. So let's see if we are still all on the same page. What are the individual letters there? So x is the state we are solving for, y is the inertia term, m was the mass matrix, h was the time step, and e is the energy potential. For example, in a mass spring system, that's just our Hookean potential, which you are now familiar with. So why is this equivalent? Finding critical points. So what are critical points? Critical points mean that the gradient of the function, critical point means that the gradient of g is 0, right? If that's true, then that's a condition of a critical point. Now the critical, you should know though from calculus that the critical points can be either local minima, local maxima, or saddle points, right? Either of them are fine. You would really be wishing for local minimum. Saddle point is very unlikely to happen, and so is local maximum. But we can just be looking for an arbitrary critical point. And why is this equivalent? It's because if I compute the gradient of g, what do I get? You should be now really good at computing gradients. And here it's very simple. So this is the gradient of this convex quadratic part, the x minus y transpose mx minus y, right? It's just this. That's why I put there the 1/2, by the way. So it disappears. What is the gradient of e? It's minus force, right? So this is minus h squared force at x. So clearly, if I set this to 0, I am back at this equation. So indeed, these two problems are equivalent. Problem 1 being solve the system of 3m nonlinear equations. Problem 2 being find critical points of this function. And what is the type of this function? The function g goes from r to 3m to r. So you can really think of it as a height field, right? If this wasn't 3m, if it was r2 to r, then it's really just a height field. And the problem is, if it was finding a local minimum, they would be just going to some point where water would hold, where there is a local minimum. This is why I sort of prefer this, what is sometimes called the variational view of implicit Euler, or optimization view of implicit Euler, a little bit better, because I find it a little bit more intuitive to be minimizing something rather than solve a system of nonlinear equations. So this formulation is what we will be using here to get a better solution for the implicit Euler time step. Okay, this variational formulation. So what we really want to be doing is computing the minimum of g x over x. The argument, are you familiar with the argument? That just means that I'm interested in that x. They're not so much interested in the actual value of the g. The value of the g doesn't really matter so much. I care about the state x, right? Once I solve this, I know then the x becomes the new time step qn plus 1, so the new state of the system in the next time step, and then I repeat the procedure. Then I go to qn plus 1, qn plus 2, and so on. All right. So when you are presented with a nonlinear optimization problem like this, when you need to minimize some complicated function, the first thing that comes to your mind is Newton's method, right? And that's exactly the classical approach. One step of Newton's method applied to this minimization problem is exactly Borovitkin's method, right? Applying Newton's method until convergence gives you the perfect solution, the exact solution of implicit Euler integration. But there are many other methods possible, and interestingly, some of them can be more efficient. So the method I would like to describe today is one of them. So maybe we could start from the simplest method, and I think Tintin discussed it the last time, gradient descent, right? So if I have some height field, the simplest way I can try to minimize it is by doing line searches in the direction of the gradient, right? So Tintin described this the last time, but I don't think he explained you. I don't think he had the time to explain you why that is actually not such a good idea. Why Newton's method is much better idea. Like, think about it. Like, let's assume you're somewhere in the mountains, right? Somewhere on the ridge or something, and your task is to find like a pool of water or something, a local minimum, right? So which you are somewhere. Which direction are you going to go? Well, most naturally you would probably go the direction where a ball would roll if you dropped it there, right? The ball would roll in the direction of steepest descent, right? That's exactly the direction of the negative gradient, right? So maybe you're thinking, why on earth I would want to be going in a different direction, right? That's the steepest one, right? Like look at it around. If there is like a mountain around you, that's the one that goes steepest down, right? Newton goes down in a different direction. It doesn't always pick the steepest descent direction. So why?
Because if you go to the deepest direction, you may go into the local minimum.
So this all is about local minimum, right? I'm totally fine with local minimum. I have absolutely no aspirations of trying to find global minimum. I know that this is like the cliche thing, don't get trapped in local minima, go for like a global minimum. In phys-based, we are almost never looking for a global minimum because we would probably never find it anyway. So that is an issue in optimization, you're absolutely right. But what I'm talking about is a different problem. So even if I'm looking just for a local minimum, that's what I sort of meant by I'm looking for a pond of water, right? It can be a pond of water which is 10,000 feet above the ground, right? So it's clearly not a global minimum, but I just want to find that particular point. So here is an example I took from Steve Boyd's book on convex optimization. So this example, so what is it showing here? Oh, what is this showing here as our color printer sucks, so disregard these lines. But what it is supposed to be showing is a function of two variables. So this is just a function from R2 to R. It's a function which is this, x1 squared plus 10 x2 squared. So if I look at isolines of this function, it's like a bowl, right? And if I look at the isolines of the function, they are ellipses, right? Clearly the local and global minimum, because it's just a quadratic, the local and global minimum is exactly the same, so I don't have this issue here. And it's at the center quite clearly, like it's 0, and it's never going to get below 0, right? Now let's assume I start right here at my x0. So my x0, that's my initial guess. You always have to start the optimization somewhere. I will tell you where to start the optimization in PhysBase, so it works nicely. So this means that we started at a point 10 and 1. So 10 and 1. Okay? So I stand right here. And I look, where's the direction of steepest descent? Well, this is the direction of steepest descent, right? And what I do a line search. I go to the minimum in this direction. So the direction is fixed, and I look for the minimum of the function along this ray. And I come here. This is my x1. Now I don't know what exactly it is, but it's like here. Here I do the same thing. Aha, now the minimum points this way, right? If I go this way, here is where I will get. And so on. And eventually I will get to the local and global minimum. But it took quite a few iterations, right? So the answer to my question, why gradient descent is not such a great idea, is because it's basically like greedy, right? Like if you're playing chess, it's usually not a great idea to always go for the kill, to always like take the biggest figure you can. That's like a greedy. That's a greedy but stupid strategy, right? So in this case, it's stupid because the gradient is only concerned about like super small neighborhood of this point, right? So it's not really looking for further ahead, and that's why it doesn't work so great. By the way, if I scaled it by more than 10, I could scale it by any number. Then the number of iterations gets higher and higher, right? I always get this zigzaggy thing that could take easily a million iterations. Newton's method on cases like this, you know how many iterations Newton's method takes to solve this? Just one. Newton's method goes right for the goal. Why? Because Newton's method does locally quadratic approximation of the function. Since this already is a quadratic function, then already one iteration of Newton's method solves it absolutely exactly. So the direction of Newton's method would be like this. That would be the direction of Newton's method. Line search, perfect line search would find this is the optimum done. Now, of course, this is a simple example. Functions we are minimizing in physics, in mass, even already in mass spring systems, they are of course more complicated than this, right? This was just like a nice didactic bowl. What you were looking at in your assignment one was just a one spring. But already if you look at two springs connected together, so a system like this, let me do it like this, one spring and a second spring, you will discover that this energy is non-convex and does not look simple like this. Okay, but I would like to finish this method, so let me move on in the interest of time. We can discuss this later. So now you might be thinking, well, the Newton's method is really good, right? So how do I want to beat it? That's exactly what we wanted to do, to beat it. There is a trick to it. So what is the weakness of Newton's method? What is the main disadvantage? It gets really good direction, right? Like I showed on this example. The direction it computes, that's really good, right? But what is the main problem with Newton's method? Problem is that computing this direction is sort of expensive, right? It requires me to compute the Hessian and invert the Hessian, right? Or not exactly the Hessian, but to be exact, what I need to be inverting is the mass matrix plus h squared of the Hessian. This I need to invert and apply to the direction of the gradient. That's how Newton's method works. And this Hessian, it will be different matrix at every step. So that you will get a new matrix to invert, a new linear system to solve. Like you never want to be, we have been through that, right? You never want to be actually inverting the matrix. It would be a total overkill. What you want to be doing is solving a linear system sort of like this. So you don't want to be doing this, you just want to be solving a linear system. The problem is that with Newton's method, the system matrix A will be changing every step. Not just every time step, but also every iteration during one time step, right? So I said as we are like here, right? When we are doing this x0, x1, x2, x3, x4, and so on, at every point, the Hessian will be different in general. Not in this simple case, but already with two springs, it will be. Maybe actually already with one spring, it will be. Okay, so what is the idea of our new method? The idea is sort of interesting. It's saying that we will not be using Newton's method, because again, Newton's method requires us to solve the system of linear equations, right? If you want to be doing it in a game, you can do it. James O'Brien did it previously, and they just use conjugate gradients. But you cannot really go to two big matrices, to too many degrees of freedom in your system. So the idea we had was to apply a technique which is called local global alternation. Sometimes it's also called as a block coordinate descent, which is basically a different type of optimization strategy. And there is a little trick to applying it. The trick is that to be able to apply this different strategy, we need to first introduce some auxiliary variables to our optimization problem. So what are these auxiliary? So we need to introduce auxiliary or helper variables. So the x, aka qn, right, which is a 3m dimensional vector, those are the primary variables. Those are the ones we need to solve for. And here I'm saying that we will introduce some addition variables. And in the case of a mass spring system, here is where it becomes specific to mass spring systems. In the case of a mass spring system, these auxiliary variables will be spring directions. So let's recall Hooke's law. I need to write down the specific formulas, otherwise it would be too wishy-washy. So Hooke's law, as you know, if I have two particles connected by a spring, then the energy potential due to the spring is this, where R is the rest length of the spring and K is the spring stiffness, right? And this is the standard Euclidean potential. Again, you should be really familiar with this from your first assignment. And here is like a little lemma which tells us how we can rewrite this as a special type of optimization problem. Here is how we introduce the auxiliary variables. So the lemma says that for every p1 and p2, the p1 and p2 are just R3 vectors, so just x, y, z coordinates. And for every non-negative R, that's the rest pose spring length. That's the length of the spring in the rest pose. It is true that if I compute the minimum of this optimization problem, so we write it down and then I'll explain it. P1 minus P2 squared minus D squared. So this minimum is exactly P1 minus P2 minus R squared. So I got rid of the K because they're just a scalar multiplication. Then that's really nothing interesting there. But what is interesting is this D here, right? What is the D? The D is just a 3D vector, R3 vector. And what I have on the left-hand side, let me put it in brackets like this. So on the left-hand side, I have a little minimization problem. The P1 and P2 are fixed, right? Here I'm saying that I can pick arbitrary but fixed P1 and P2s. And the D is my auxiliary variable. This is what I was talking about here. Those are the auxiliary variables. Now the auxiliary variable D is the spring direction. So the D is the vector of the spring direction, and it has to have the length of the rest pose spring. The length of the spring at the rest pose. That's the R, right? So I guess I could look at it like this. If I have my spring, this is some current configuration of the spring, and if the rest length of the spring was like this, then my D vector would be a vector like this, right? This would be P1, P2, and this would be my D vector. Okay? Interestingly enough, if I minimize this function subject to this constraint, then the value I will get is exactly this. So that's exactly the potential up to this scalar, but that's not interesting. I can always multiply, right?
Oh, I'm sorry. I have a question.
Uh-huh.
The P1 minus P2 square is a scalar?
Oh, yeah, you are absolutely right. What I wanted to say was like this. Yeah, very good point, actually, made there. There is no squared. Just P1 minus P2. Let me double check with the paper. Yeah, thank you for catching this. Right, there is, yeah, it was not making sense, right? So indeed, yeah, very good point, thank you. So indeed, I am just subtracting vectors here. So this is P1 minus P2 minus D. I wouldn't even need a bracket here. Just put there the bracket to make it better readable. Now what here it's different, right? Here I'm taking P1 minus P2 and taking the norm out of that. And here the R is a scalar, here the D is a vector, right? Make sense now? Thanks a lot, great question. Not obvious at all. So I think in the interest of time, I will leave this, the proof of this lemma for homework. It's also in the paper. I mean, it's not a real homework that you have to do. It's a homework that you can do. It's really not difficult. You just analytically minimize this directly. Maybe I will do it if I still have some time at the end. I just wanted to explain you how this thing helps in solving the implicit Euler time step, right? So the problem of solving implicit Euler time step is equivalent to minimizing, I will just forget about the arc, let's just write we are minimizing the gx, where the gx is, let's remind this, is this function, right? And what I use this lemma for is for rewriting this e. So this minimization problem can be also written as minimizing some slightly changed, slightly different g, that's why the g tilde, which has variables x and d, subject to some constraints on d. So here by d, I mean aggregated d, so this is d for an individual spring. Here I mean by putting it for all springs together. I will write it down correctly, or for formally correctly. So if I have S springs, that's the number of springs, and the indices of the endpoints of spring are I1 and I2. Those are the indices of endpoints of spring I, where I goes from 1 to S. Ki is the stiffness of every spring, or Ki is the stiffness of spring I. So the key idea here is to use, so instead of using this, I can use this because they are equivalent, right? This is exactly the Huygens potential, and this is equivalent to it. So I will use this formulation. This will introduce the auxiliary variables D subject to this constraint, and then I will be minimizing with respect to both X and D. So I sort of like put there some extra variables into the optimization problem, and then I minimize over both X and D, and magically this will make the optimization problem easier to solve. So the potential here becomes this. It becomes, after I multiply this back by the constant K, so this becomes Ki Pi1 minus Pi2, so I will not even bother with the bracket here, minus Di squared. So here I am using this formulation, using the auxiliary variable Di, that's the direction of spring number I, and those are just the endpoints of the spring. So this is my new potential, which uses this auxiliary variables D. So if I minimize this subject to the constraints that the norm of every Di is equal to Ri, where Ri is the rest length of spring number I, then this is equivalent to the original Huygens potential of all the springs. Now this can be written very elegantly using matrix form, and it looks like this. So this is just the same formula, just rewritten in matrix notation. If you like using MATLAB, that's what you are doing in MATLAB all the time. So what is X here? X is a vector which stacks all the p's, all the particle positions, right? P1, P2, to Pm. So it's a 3m by 1 vector, right? What is D? Well, obviously it's a vector that stacks all the D vectors, D1 up to ds. And this is a 3s by 1 vector, right? So this sort of tells you also what are the dimensions of the L and J matrices. All right. And J matrices. I'm debating if I should go into the details of how the L and J matrices are constructed because I don't have a ton of time. So let's just let's just say that these L and J matrices are constant matrices, and you can derive them by reorganizing this formula. Maybe we'll get to that later. I would really like to finish this method now. This is also where the Kronecker products will step in. You know what? I can write the formula for L. Let's do that without actually deriving it. You can derive it for your another homework, which you don't have to do, so you will probably not do it. So what is AI? AI is an indicator of a spring, so, or spring endpoint. So it's a vector that has all zeros except for 1, 1 and 1 minus 1. And this 1 is at position I1, and this minus 1 is at position I2. So this is the L matrix. The J matrix is similar. The J matrix looks like this. It's sum over I from 1 to S. Okay, I, AI, SI transpose, chronicle I3. Now you should be asking me what is SI, and SI is the indicator of ith spring. So it means all zeros except for 1, 1 at position I. So SI is RS times 1. And AI was obviously M by 1. M by 1. All right. And believe it or not, this is exactly with the matrices defined like this. This is exactly equivalent to the sum. So why I'm doing this? So I don't have to be dealing with the sums. So I get a nice concise matrix expression. All right. So if I'm simulating a mass spring system, then my potential, if x is the state, arbitrary state, then the potential was just the sum of all individual springs, right? So going over all springs from 1 to S, taking the stiffnesses nicely into account, and this is the standard Euclidean potential minus Ri squared. So I can write it using this result I just derived. So using this. Sort of cool. So I can write it as a minimum over D from some set U. I will specify that in a second. And here is this. 1/2 XTLX minus XTJD. And the set U is the set, you could probably guess it, D1 to DS of all spring directions which satisfy the constraint that the DI vector has length Ri. Right? Every spring can have a different rest length. Those are the Ri's. Ri is the rest length of spring I, and these are my auxiliary variables. Now the auxiliary variables cannot be arbitrary. They are constrained to have the right length, and this is what is encoded in this set U. Okay. Now in addition, so this E that can completely encode all internal forces in my system, I can also have external forces which are sort of easy, which are easy to add there. I can just say that this is Ex plus X transpose F external, where the F external, there can come gravity, collisions, friction, and whatnot. And we can now plug this into our gx function. Where was my gx function? Here. Oops. Here. This is my gx. So what I'm going to do is I will just put this into gx. So let me write it again here. So the gx, then I substitute for the E is going to be this is going to be the same, 1/2 X minus Y transpose M X minus Y, and I will have plus, oh, you know what, I will do it, this is gonna be the G tilde with X and D. Okay, let me write this nicer. G tilde X and D is this, okay? And here I will have 1/2 of h squared xdlx minus h squared xdjd. And I can also plug, if I have external forces, I can also put there h squared xdfx. That's this term. That's the potential term of external forces. And now the implicit Euler time step is equivalent to minimizing the g tilde of x and d, subject to the constraint that my d is in the set U. And of course x is in R3, but 3m by 1, but that's obvious. The difficulty type when you are standing. So we are minimizing this function, which is now dependent on both x and d. And here is why it's called local global alternation or block coordinate descent, because I'll be alternating between optimizing over x and optimizing over d. That's the key part. So the first step will be fix x, freeze x. X is gonna be fixed now, and optimize over d. So because now you can see why I introduced these auxiliary variables at the first place, right? Because I can now play this ping-ponging between x and d. So in this first step, I just say that x, whatever x was in the previous step or from the initialization, that's not gonna be changing. The x is gonna be frozen. And I'm gonna be working just on the d. So I will minimize this function with fixed x, and I will find the optimal d. So that is actually very easy, right? If you recall what the d is. The d is the rest length spring direction. So this step essentially means just to normalize every spring, right? Just project every spring on the rest length, just as I draw the picture before. If I have a spring like this, there are some other springs, of course, connected to it, but I'm not concerned about it because I have d for every spring, right? d1, d2, d3, and so on. For every spring I have a d, right? So if this spring is stretched and should have really been shorter, then what that means is that after doing the local step, my d is going to be shortening of this spring, if you will. So formally, I guess I could write it as P1 minus P2, or PI1 to be really super correct. PI1 minus PI2 divided by the length, multiplied by the rest length of the spring. So this is gonna be my new DI. So that's the local step. So I do this for every spring, right? So this spring also gets, if this all was stretched, or let me draw a better example. If I have something like this, and all the springs were overstretched, then this is essentially, those are my springs. This is essentially saying that every spring goes back to its rest length, right? And I don't care here that the springs are connected, because every spring here is by itself. Right? So every spring I project back to its rest length. I don't change the direction, I only change the length. Okay? And this way I get the new d's. Those are the new d's. Those are the vectors of the rest length springs in the right direction. And here comes the second step. Here I will, guess what, fix d and optimize over x. So you can also look at it this way. The first step basically disconnects the system, right? These were my particles, and the particles are no longer being respected, right? That the springs just got projected back without taking into account the fact that this should have really been the same point. So guess what? So this is the local step, and this is the global step. The global step puts it back together. The global step means that after I have fixed the d, what happens after I have fixed the d? After I have fixed the d, then this becomes This becomes constant. And I'm left with solving a convex quadratic optimization problem, unconstrained, right? The constraints are only on D. So if I have a fixed D and optimizing over X, I'm solving an unconstrained convex quadratic optimization problem. What is the Hessian of that problem? The Hessian of that problem is m plus h squared L, right? That's because the unknown here is X. So here is the quadratic term in X. That's xtmx, 1/2. And here is the second one. That's 1/2 h squared xt lx, right? So the Hessian is m plus h squared L. You can show that this is symmetric and positive definite. It's because the Laplacian is positive. L is the Laplacian matrix, and it's positive semi-definite. If I add to it the diagonal matrix M, it becomes positive definite. You can prove this relatively easily. So the global step means that I need to solve this linear system. So here the B is some right-hand side where I gathered both the external forces. I put there the JD. The B gathers these linear terms. There's the JD and the Fx. So the B depends on every state, right? The B depends on D. B is my right-hand side here. So it might look like that I haven't really helped myself much, right? I just deployed a different optimization technique, and here I again end up solving a linear system, right? Now, what is the big win? The big win is that this linear system does not change. This linear system is the same at every step, because the M are the masses, right? So as long as the masses are not changing, the M is constant. And the L is what I defined here. The L is essentially the Laplacian of the graph of the mass spring system. Yeah, sorry, I didn't really introduce Laplacian. I don't really have the time for that. We'll get to Laplacians in some next lecture. Take it just a buzzword for this matrix. The point is that the A's and the K's, they depend just on the structure, just on the layout of the mass spring system. That means that the L is a constant matrix. It will not change unless you add there some more springs or add some new particles. But most of the time, this m plus h squared L is going to be constant. So that means that we can efficiently prefactor it and solve this system for different right-hand side B's. The right-hand side, the B's, they will be changing every step. But the system will not. So you can think of it as basically, you could as pre-computing the inverse, except that you don't really want to pre-compute the inverse because this is a sparse matrix and the inverse would be a dense matrix. So you cannot really do that directly, but you can do it indirectly through sparse Cholesky factorization. But that's almost the same thing as pre-computing the inverse. You can think of it that you pre-compute some structures so that you can very quickly solve systems of this form. And before I let you go, I will just show you real quick the results in terms of convergence speed. So how does this compare to Newton's method? So this is what we did, and here it looks like it compares absolutely terribly. So this is our method. This is how quickly it converges. This is the error. So the lower you are, the smaller the error. Newton's method, you can see the quadratic tail. This is a typical behavior of Newton's method. It goes really quickly to the solution, right? In the number of iterations. So here it looks like that we are absolutely losing, right? We are like converging really slowly compared to Newton's method in the number of iterations, right? But mind you, every iteration of Newton's method is much slower than a single iteration of our method. It's because every iteration, every one step here in Newton's method requires us to solve a different linear system. We cannot pre-compute there anything. So if we look at the same graph where on the x-axis is time instead of number of iterations, all of a sudden it changes quite a bit. Our method starts winning over Newton until some pretty high accuracy. So if you want super high accuracy, you want like machine precision accuracy, if you want precise result to like 6 decimal digits or something like that, the Newton method is still the better choice. But if you don't need as accurate result, then our method will get there faster than Newton's method. And this is the case in physics-based simulation, right? There is absolutely no need to compute it to like 6 digits of accuracy, because all we care about is the visuals, right? So if the cloth is a little bit off by a couple of millimeters, that doesn't really matter that much. What matters more how quickly you can compute that. Okay. Any questions? Okay, so I think that's it for today. Thank you.